Hello everyone, November the 3rd. I think we have done this problem before. Doesn't matter, let's just get through it really fast and then try to roll another one. Yes, exactly, that is the spirit, honey. Some root to leaf numbers. I think it's what, sum all the values from root to a leaf? Is that what it is? Maybe last year. Wait, we haven't done this before. My guess has been wrong for so many times. Alright, I've not done this before, so it's a new one. Given the root of a binary tree containing digits from 0 to 9 only, 0 to 9 only, how many nodes do we have? 1,000 nodes. Depth of the tree will not exceed 10. Each root to leaf path in the tree represents a number. Oh. So root to leaf, for example, the root to leaf 1, 2, 3 represents 1, 2, 3. Return the total sum of all root to leaf numbers. Test case is a generator so that the answer will fit a 32-bit integer. A leaf node is a node with no children. So this is 1, 2 plus 1, 3. 4, 9, 5, 4, 9, 1, and 4, 0. I see. So the idea is going to be, I think we can do BFS, right? BFS, so starting with 4, and this will be 49 plus 40, right? Oh, we have to record the number. Okay, record the number 49, 40, and then the next one, this will be what? 495. And this one doesn't have, and now we push it in. Okay, I think DFS shall suffice. Not DFS, I was thinking about BFS. DFS of both work. Maybe we can write both. Right, both works. So right now I have my mind on BFS, so let's try BFS first. Again, it's a tree, so we do not test. Alright, so this is going to be, let's say, BFS, right? So when I have a Q, it's going to be this, root, alright, and then we have a res equals 0. And what do? We do, actually, it's going to be root and, so we're going to have two things, right? And all this is a value, so root.val. What if it's an empty root? 1, so it's not going to be empty root. So we say while q, right? Temp is equal to this for node val in q, right? If not node.left and not node.right, then res plus equal val. Else if node.left, then temp.append, right? Append what? Val times append node.left and val times temp plus node.val. And do the same thing for the right and node.right. Val times 10, same thing. So blah blah blah, and then q equals temp. Once it's done, return res. All right. Let's see if this one works. Let's run the test cases. Take exactly 1 hour. What did I do? Oh, my bad. I forgot to put another parentheses around. It has to be a tuple. Nope. Huh. How did we get it wrong? So we got 12 We got what? 25. No, we got 22. Huh. We got a bit less than required. Hold on. So we start with 1, right? And then pop out if on the left, then temp.append. It's the append to this, right? Next one on the left, and then the current value is going to be the val times 10, which is 10, plus this is 12. So when we visit this, is going to be 12. So rest plus equal to 12. And then if node.write, it's going to be 13, right? So Q equals temp. And back up. So node and val, node is going to be this. And then val is going to be 12. And I say, okay. Oh, node.val. Nah. I see the problem. It's not node.val, it's node.left.val. My bad. Node.left.val. Node.right.val. Node.val is already inside, so we don't have to do it again. There we go. This shall be right. All right, let's submit this. Okay, 488. 488 days. Yeah, once we reach 500 days, we're gonna celebrate. So it's yeah, BFS. At each node, accumulate the number. Accumulate the number so far, right? Accumulate the number so far. Aggregate the result when a leaf node is encountered. When 24. We got a 96. All right, let's try a DFS. So this one's a BFS, right? So LeetCode, I think 129. Is that 129? Yeah. So let's try another one. So another one will be BFS, not DFS, right? So DFS, similar idea as above, right? We can actually put it here. I don't have to start a new line. All right. We don't know about this yet. So how do we do some numbers? We're gonna have self.res, right? Let's start with this, and then def DFS. We have a node, which is optional. Actually, it's not going to be optional, but that's fine. Let's just do optional. Tree node and current val, right? Current val. We need current val. And then we return nothing, and then we say if not node self.rest plus equal val, else DFS, which is called node.left val times 10 plus node node.left node.val. So we do a little bit differently. So node.right, I'll go to the right, and then we add myself. So when we start, we don't add anything. And then we call it DFS. What do we call DFS? DFS root, right? And starting value is 0. And then return self.res. Let's see if this one works. Yeah, let's see why not. And nope. 50. val times 10 plus, so we start with this, right? And then we say we're gonna go left. And when we go left, the val passed in is going to be, val is 0. So it's going to be 1. So passing here is 1. So 1 comes in, and I'm going to go left. Oh, I see. Because I did it twice. Alright, I cannot do it that way. I have to, and if not no dot left and not no dot right, then we do this. Else, yeah, I think we ended early. Let's see. We ended early. One step early. That shall work. We end one step. No. No. One step early. I cannot do that. I have to say 10 times because the val I have not included myself yet. Right? So plus no dot val. That one feel like, yeah, this is correct. Okay, but I want to change a few things. Alright, so what do you want to change? First of all, I can say a current, right? I can set up a current. And if this, then we return current, right? I'm gonna return an integer. Else, when I return, how about left plus right? Yeah, how about that? So, but these are all current, right? And in that case, why don't we just set up a val, right? For 0, so passing is 0. And then we simply do this. Hold on. We simply do this. Current equals this. 10 times val root dot val. And all the node turn into root. Right? Turn self dot sum numbers. Alright, val equals self dot sum numbers. Val equals. And yeah, let's try this. Let's see. Yeah. I think this one. Runtime error. Object has no attribute. Huh. Why is that? Because, okay. Alright, so that is not working because we need to say left equals, hold on, I don't need to. I just say if not root, right? If not root, we're just going to return 0. Otherwise, we do this. Yeah, let's put this in. 0, 1. Yep, it's correct. There we go. That's good. This is good. So I have 2 solutions for this. Yeah. So this one, we don't need this anymore. DFS. Okay. That's it. Nothing too special. I think they will all have like BFS and DFS. DFS. Yep. Yep. That's about right. Okay. We don't need to upvote for this one. We just do this. All right, we're done with this. Let's roll another one. So we spent 15 minutes on this. All right, I'll roll another one. All right, pick one. What we're gonna have. Global and the local inversions. I've done this before. In April. Nope. Let's try another one. Oh, the laptop is too slow, so it takes a long time, even just to roll. Maybe it'll be easier for us to search a value. Let's go random number generator. We have 2060, right? So random number generator. Let's generate 10 values from 1 to 2060. All right, 957. All right, let's see, 957. I don't think this is any. We did it. No, I don't think this is any easier. Maybe it is. I mean, let's roll again. 1768. 1768. That's an easy. Now we don't want easy. Generate again. 83. 83. Yeah, this is not working. This is not working. We have to use this. But it doesn't. Can I open it in a new window? I can. I have to just roll it on the same page. What are the likelihood that I'll roll another one that I've done before? We can calculate that. Grand Slam. Oh, subscribe to unlock. So they do not prevent this from happening. Yeah, so what the hell? They do not prevent this from happening, so it's actually easier for me just to check the number. I'm gonna roll random number from here. So from random import rand int, right? And then we're just gonna do rand int from 1 to 2060. Right, for this in range. Let's roll it 10 times. So 10 random number. So 85, I think I must have solved 85. So we can try. Oh, I can do this. Ah, 85 is not a medium question. 954. 954 solved before. 1128. Not a medium question. 1870. There we go. 1870. Yeah, which one will be faster? I think this is faster because we are not opening a new web page. It's just searching through their database. So I think this is faster. Yeah. Okay, minimum speed to arrive on time. You're given a floating point number hour, representing the amount of time you have to reach the office. To commute to the office, you must take n trains in sequential order. You're also given an integer array dist of length n, where dist I describes the distance of the ith train ride. Each train can only depart on an integer hour, so you may need to wait in between each train ride. For example, if the first train ride takes 1.5 hours, you must wait for an additional half an hour before you can depart on the second train ride. At the 2-hour mark, return the minimum positive integer speed in kilometers per hour that all the trains must travel at for you to reach the office on time, or -1 if it is impossible to be on time, such that the answer will not exceed 10 to the 7th. An hour will have at most 2 digits after the decimal point. Oh, as a floating point. Okay, at speed 1. 1 plus 3 plus 2. 2.7 hours at speed 3. The first train takes this amount of hour. When not at an integer, we wait until 1 hour mark to take the second train takes 1 hour, so we'll have 2 hours. So already at integer, we depart immediately at the 2-hour mark. The third train takes 0.667. It will arrive. Ooh, this is an interesting question. 1.9 is impossible because the earliest third train can depart is at the 2-hour mark. This is a good intuition, right? So no matter how fast you travel, this train only. So we have a lower bound, right? So if we have 3 distances, and the first distance, no matter how much time you take, this one has to be taken in the hour 1. This is hour 0, hour 1, right? And then the fastest can take is hour 2. So if any hour is smaller than length minus 1, that is impossible, okay? So that's one insight. Okay, so now we're trying to figure out how much we need to take. Distance, right? So we have a total hour, and we want to find a minimum positive integer. I mean, of course, if we go, we go berserker on it, right? And we'll take the same number of hours. So that's not what we want. And we decrease it, right? When we decrease it, and every train will travel at the same speed, right? So if we decrease it, like we find a maximum, right? We find a maximum, then it will arrive at speed 3, so 2.6 hours. Oh, it's actually smaller. It's actually smaller. It's 2.6, right? So what's the smallest number of time? Well, this is the second hour, so the smallest will be, this will be 1 hour, all right? And then you take this for 2 hours, and then, so it's n minus 1, right? It's n minus 1 hours is the minimum, so it must be larger than n minus 1 hour, and smaller to whatever value. And even if we take gigantic amount of speed, we'll definitely have to take 1 hour, 2 hour, and something, right? So the minimum time is n minus 1 plus the last speed the last distance divided by speed. So this is the minimum amount of time. So we can actually, that's 0.7, right? And we know the minimum amount of time to start from here is 2 hours, which means the last trip has to take 0.7, right? 0.7 to cover 2. So if we do 2 divided by 0.7, what we have is 2.85, right? 2.85. So that will be the requirement for the last trip. Yeah, no matter how fast you go, this is, when you hit here, it's going to be a 2 hour mark, right? So based on this, you can get a little bit estimate. The estimate is 2.8, right? So it's going to be 2.8, 5 speed. And then we'll go back and see if this trip going 2.85 it must be smaller equal to 1 hour, right? Smaller equal to 1 hour. So we try 3 divided by this, and it's larger. So 2.85 does not work. We need to be a bit faster, right? So the minimum speed will be 3, right? So it's going to be 3 and 2.8. Minimum speed is 3. And then the minimum speed of the last one is 2.85. So the minimum speed is 3. Okay? How about this one? Hour is 6, right? So we have 1, 3, 2. So we know the minimum amount of time to reach will be but now we have 6 hours, right? We have 6 hours. Now we have 6 hours. And based on the number of hours, we can add up the distance. We add up the distance. Right? And then we know if the train goes at speed 1, now the total number of hours will be the total number of distance added together. So that can be a bound. So we have a bound, like a higher bound, right? Higher bound. And then we check the total allowed time. If the allowed time is equal to, then that's done. If the allowed time is smaller, then we know our speed has to be faster. And then we'll also have a lower bound, right? We have a lower bound. It's going to be n-1, larger than n-1, right? So if it's smaller than n-1, then that's impossible. So if the value is in between n-1 and added together, then we have a certain speed in between. Okay. What if it's larger than added together? Then the speed can be even smaller, right? And the speed can be even smaller. There's 6 kilometers in total, right? 6 kilometers in total. We have 2.7. So the average speed is 2.2, right? 2.2, which means if it's that's including the wait time, right? It's 2.2, which means if it's slower than 2.2, that is not possible. Yes. Wait, it's slower than 2.2. Yeah, it's much slower than 2.2. It's definitely not possible. So that's like the speed lower bound. Speed lower bound is just going to be the total distance divided by hour. That's the speed lower bound. No, I don't think this speed lower bound means anything. No, I don't think that means anything. We're just n-1 the time. We'll have the time lower bound. Oh, actually, don't have a time upper bound. Time upper bound is just the hour, right? That's the hour. So what, binary search it? Can we do that? Like, I think speed has to be an integer. Depart integer time. Positive integer speed. Yeah, it has to be integer. Okay, so I have hour. So we say we take the middle hour, and we just want to see if it's possible. But we have a 10 to the 5th. So O and log n. Maybe O and log n will work. So we have a lower bound, we have an upper bound, and then we find the middle ground. So we want to arrive within the hour. So we find the middle ground, which will give us an hour, right? We have an hour. And what we just go through everything and see if it's possible to reach that hour. Let's use the first one as example. So we know the lower bound is 2. higher bound is 6. So in the middle is going to be 6 plus 2 divided by 2, which is 4. Let's say we want to do 4 hours, right? And we want to check if 4 hours is possible. If it's possible, then we can search for higher. So 4 hours, how to make it possible? How do we check if it's possible? 4 hours. Well, 4 hours. Huh. 4 hours. Yeah, how do I check if it's possible? Well, it boils down to this question: how do I check? Well, the first trip, let's say each trip would take at least 1 hour, right? So the first trip would take 1 hour. Second trip would take 1 hour. Let's say each trip takes 1 hour, right? Because all we are checking is the feasibility. Let's say every trip takes 1 hour. So we have the minimum. Actually, no, the maximum. So we get a maximum value among them, right? No. We try to fit 4 hours to it. How should I do that? I try to fit 4 hours. Cannot divide it evenly. Each trip takes at least 1 hour. Yeah, each at least takes 1 hour. But if we slow down, it'll take longer. Yeah, basically, can 4 hours be possible? No. A 4 hour be possible. We actually want to find a speed that can make it larger or equal to 4 hours. How? How? We can we sort it? No, we cannot, because it will affect the waiting time. Well, any time the highest impact will always be the largest value, right? So I'd say I'll look at 3, right? 3. In order to make the total time smaller than 4 hours, and then we know at least it will take 2 hours, right? So at least it will take 2 hours. And we are saying we want to try 4 hours, which means the extra time, the time used for actually traveling, is 2 hours. Like additional traveling time can be 2 hours. So we can say, let's use that 2 hours on the longest. Doesn't feel right. What is the logic here? Or we should go the other way. Now, not go the hours, we go the speed, right? Well, we know the maximum distance is the speed. So we take the maximum distance, 3, right? This one we just say, my speed is 3, right? My speed is 3, that's my starting point. And the lower bound is 0, which is I'm not moving at all. So that's the speed is to 0 to 3, because anything larger than 3 does not make any difference. And 0 will be infinite hour, but 3 is going to be 2 hours, right? So with 3, no, it's not 2 hours, 2 point something else. So 2 divided by 3. So 2.67 hours. That's if the speed is 3, which is the higher bound. So anything larger than 3 is just, it's not necessary. And then we binary search. So we go 0, 3, so it'll be 1.5, right? So 1.5, let's see like how 1.5 is going to do. Okay, so 1.5 is larger than 1, so the first trip will take 1 hour. And 3 divided by 1.5 is going to be, I don't know, 3 divided by 1.5 is going to be 2. The second trip will take 2 hours. The first one is 1 hour, second is 2 hours, and the third, 2 divided by 1.5 is going to 1.3 hours, so plus 1.3. So that come up to 4.3 hours, right? Which is smaller than the hour needed, hour 6, which means our speed can be slower. So we search again, 0 to 1.5. But hold on, we want the minimum positive integer, so we actually get the integer out. So we get integer out as 1, right? And I believe these values are integers to start with. Or be almost 2 digits after the decimal point in hour. No, that's not what I want to see. I think the kilometers are also all integers. Integer array dist, yeah, so it's also integer. So the higher bound is going to be integer. So we just find an integer. So find an integer is 1, right? And a 1, a compute is going to be 6, which is exactly, so 1 is the answer. If the hour is larger, no, hour is smaller, hour can hour be larger? No. Wait, it might be. It might be. The hour might be larger, all right? So, but anyway, with binary search, so 1 that comes in, and if the value is too big, that means that if the value is bigger than the required hour, that means we need to bump it up. If its value is too small, that means we can slow it down. So which exactly happens here, right? We start with 1, give us 6. 6 is larger than this, therefore our speed need to go up. So go up is going to be from 1 to 3. So 1 to 3 will give us 2. So speed is 2. So now speed is 2. The first one still takes 1 hour. Second one takes 3 divided by 2. And I think we're going to use a ceiling, right? A ceiling. So that's actually 2. And the last one is going to be 2 divided by 2 is 1. So that's 4 hours. Speed is 2 is going to be 4 hours, which is still larger, so we need to bump it up again. So we're going to be 2 plus 3 divided by 2, but we're going to employ a trick. It's going to be 2 plus 1, right? Because there's always bias. We're biased towards the lower end. So we're always going to do plus 1 divided by 2. Oh, should we do plus 1 divided by 2? Because 0, 3, if we do plus 1, that's going to give us 2. And then 1 plus 2, that's going to give us 1. That's fine. Let's do one more round. So 2 plus 1 plus 3 divided by 2, which gives us 3, right? And then that is absolutely the last one. That's absolutely the last one. And a 3, pump in, boom, it works. End of the story. So you don't have to worry about it. Okay, so I think we have a strategy. It's going to be O1 login, and we are going to try it. So this one is 1870. Right? Nope, nope, no. I want to do this. 1870. All right, so 1870 it is. Let's get this thing rolling. Alrighty, so what do we have? We have this, right? And we're gonna say speed upper bound, right? But first of all, if hour is smaller, we say if hour is smaller than, I'm gonna len, n equals len, distance, right? So if hour is smaller than n minus 1, actually smaller equal to, because it cannot be n minus 1. Like at least 2 point something, right? If you go really high to 2 point something, so if hour is smaller than this, then we immediately return minus 1. It's impossible. Otherwise, that means it's possible, and then we need to get the low. Low is 0, right? High, when the low and high, 0, and the max dist, right? And then we say while low is smaller than high, okay? While low is smaller than high, mid equals low plus 1 plus high divided by 2. And I think Python math ceiling. The ceiling is 2, 6, 23, 10. Yeah, so when you use math, so when I import math. Anyway, so that's the mid, right? And then we're just going to go through the entire thing. I'm going to say, what should we say? We can use reduce. Now we're going to say time equals sum for d in dist, right? For d in dist, and I'm going to call math.ceiling d divided by mid, right? The distance divided by this. I'm going to say if time is larger, time is this. We'll say if time is larger than hour, right? If time is larger than hour, that means we're too slow. We're gonna get faster. So how do we get faster? Oh, we don't have to change it here. How do we get faster? We go low equals mid plus 1. That's how we get faster. Else, if it's smaller, time is smaller. Well, if time is smaller, that means we need to get slower, right? So low will equal to high. So we go slower. And then we'll come back. What if time is equal to? What if it's equal to? The chance of equal to is very small, so we don't have to think about it. We just go like this. If it's larger, then we definitely need to get faster. So we'll go mid plus 1, right? I'll try it again. If it's slower, then if the time is smaller, which means too fast, I'm going to go slower. So the low equals high. What the hell is this? High equals mid. We'll bring the high down. All right, we'll bring the high down, and then we'll try it again. Eventually, this will converge, and we're going to return low, right? Return low. Okay, let's try this. We have 1, 3, 2, 6. Answer is no. Answer is 1. 1, 3, 2. 2.7. Answer is 3. And the last one, 1, 3, 2. 1.9. Answer is minus 1. We have a dist, we have an hour, we have a min, speed on time, dist, and hour. Division by 0. Holy guacamole, what the hell happened? Mid go to 0? Hold on. Yep, I think mid goes to 0. Let's print low, high, and mid. Just give me, let me see. 0, 3. Yep, we're having a problem. We're having the problem. What do we do? 0, 3, right? That gives us 1. And then it's equal. Then high equals mid. So high becomes 1. It seems like we have to go low plus 1. This is going to be 0. And we divide by 0. The mid, like we'll always go low plus 1 and do this. Can we change this? Because the first one is 1, right? So answer is 6. The time is here, is equal to hour, right? Which is smaller equal to hour. Huh. But then if I add 1 here, I already add 1 here. Time is larger than hour. I'm too slow. I need to be faster. So mid doesn't work, so I go mid plus 1. Right? Low, I go mid plus 1. And then they will break out if they're equal. Otherwise, if they have 1 in difference, so in here, now 1 in difference, like 2, 3, that will go 3, but it will not go 2. Otherwise, we'll go for 2. And then, oh, come out. Yeah, the condition. How do we handle the condition? Because this is biased towards the left. If I plus 1, then it will be biasing towards the right. And because y biasing towards the right is good. Let me think. Mid. Yeah, we cannot. This is definitely not right, because if low and high, they are 1 in difference, right? 1 difference. And this will be 0, right? Then if it's 0, it's always going to be too big. And then low will equal to mid plus 1. I think it's just a 0 issue, right? So we can just say if mid, right? If mid equals 0, because mid equals 0, the time is infinite. So if mid equals 0, or this is larger than hour, right? If this is larger than hour, then we do this. Right? Now we pass. This apparent take some time to compute. All right? Okay. So because if mid equals to 0, that means speed is infinite. So we can do this. Try it. Wrong answer. Wrong answer. Huh. Okay, let's see. Oh, I think I know. It's the last one. Holy guacamole. I think I know. It's because the last one. Required is 2.01. And then we have expected is a gigantic value. The high bound, right? The high bound, I set the high bound to be this, but it's not. I think it has to be separated into two different categories. So this will work for the category where, yeah, because this is the problem. So we have 2 hours. So we know this trip will take at least 1 hour. This trip at least 1 hour. So that means the last trip must take whatever this amount, right? And or we can say using the fastest we can go, which is doing this. 1 hour, 1 hour. This will take actually 1 hour, right? That will actually take 1 hour. So this is 3 hours. So if you take the largest value, oh, it depends where the largest value is. If we take the largest value, we're going to check on the last one, right? And then we know the scope of this problem, right? So we take the largest value, and then we know before traveling the last piece, if you take the largest value as speed, we're going to have n-1 hours. And then we're going to plus the last one divided by the largest speed. So that is the current if our upper bound is the largest speed. This will give us a time. And then we compare that time to the hour. If that time is smaller, right, than the hour. If the time is smaller, that means our speed can be lower, right? If the time is smaller, that means we go very fast. So our speed can be lower. Then we go into this part. Otherwise, if that is still larger than the hour, right? If that's still larger than the hour, that means we need to pump the value up. Oh, I see. I see what you're saying. I see what you're saying. So we're going to do this, all right? And we're going to do this. Then we're going to check. We're going to say if n-1 plus high divided by, not high divided by, it's going to be dist, the last one, divided by high. This is the current smallest time. If this smallest time is still larger than hour, right? If it's still larger than hour, that means the speed must be larger than the max dist. Then we're just going to return what? Return hour minus hour minus n plus 1 divided by dist, last one, all right, divided by this last one, and this will give us a speed, and we want to be smaller. All right, so it's hour. No, distance divided by hour. Come on, man. How do you compute speed? This. Right? So this divided by hour, that's our speed. And we want the speed to be an integer. Right? If it's a lower, it's not, so it's going to be ceiling as well. So we do math.ceiling this as well. Okay? No, that means it's not ceiling. How? How is it not ceiling? So I need to arrive at 0.01 hour, right? And the distance is one, whatever, like 10,000. And divide by that, we have an integer, right? What if I cannot be, what if it's not an integer? Oh. Like what if let's say it's 1,000, that's 100, right? 100 divided by 0.01 is 10,000, okay? What if I cannot be divisible? I would be like 0.03, right? So let's say I need to arrive in 0.03, and then the speed I calculated is 3333 and 0.3333, right? So if we go 3333, if we say 100 divided by 3333, it must be smaller or equal to 0.03. That's not smaller than 0.03. What's the rules on the at most 2 digits after the decimal point? At most 2 digits. In this case, we need 3334, right? So we compute an integer or compute a value, and after we compute the value, we need to check if this value is integer by itself. If it is an integer by itself, then we don't do it. I mean, I think what we do is what does it say? Potentially it's going to be this value. Let's just like double division, right? And then we're going to say we're going to return part if this divided by part is smaller or equal to hour minus 1 minus n plus 1, right? Else we're going to return part plus 1. That is not fair. What the heck? I do a double division. Part. No. To another one. No, that's not a reason. Wait, what's part? Potential. Huh. I thought it's integer division. Yeah, we need these to be integers. So how about we just because this is not integer. I see. So we're gonna go math.floor. Right, we're gonna floor this. Actually, we don't need to floor this. Let's just integer this, which is floor. So we integer this, and then try this. I guess this is false. What the hell? 0.01. And then hour minus n plus 1. Oh, Lord. It's a floating point. Jesus. Can we don't know. How do we handle this? Close to. Close to. In Python has it. Close is close, right? Window is close. Okay, so we're gonna do if this. So potential is this, and then last time or equal to, that is going to be whatever this is. And then target last time, right, equals to this. So target last time, and then we say target last time, and then actual last time. And we say if actual last time is smaller than target last time, or math dot is close actual last time and target last time, right? So if they are close, well, first one is this, that will return pot, which means it's good enough. Then we will pass this one. And the other things shall all pass as well. All right, let's try it again. All right, try it again. We're close. We're close. We're very, very close. I think we have to use the same technique for the other as well. I think I passed some, right? I'm not. Yeah, I almost passed everyone. So I think this is probably. Okay, so it's supposed to be 541, right? Not 542, but I'll run. That's the problem. Oh. 2571.83. What? I got 52. No. The heck? There you go. All right. I think we're gonna fix this. Okay. I don't like. I'm gonna remove the last time. Just make these a little bit nicer. All right. That should work. And then if this return, otherwise we're gonna do this. Blah blah blah. If this is larger than, that's fine. Else, the result is 542. Actually, it should be 541. I do know one thing, that this has to be not the last one, right? I should not include the last one. So sum this plus this last one divided by mid. There we go. That's the, yeah, because the last one is not a ceiling. No, last one is not a ceiling. All right, let's see. This effort shall work. Come on. Give me some. Give me some. Let's go. Let's go. All right. So this is quite interesting. This is an interesting problem. The key insight is binary search, right? But to arrive at the boundaries, right? Boundaries of binary search, we need to do a bit pre-processing, right? Pre-processing. So first of all, we know the lower bound of time. If we travel at light speed, right? Light speed, then the entire journey cannot be shorter than n-1 hours. This means if the target hour is smaller than n-1, smaller or equal to, right? Smaller or equal to, that is impossible. Then we can pick the smallest large speed that enables us to travel at enables us to take at most 1 hour, right? At most 1 hour between 1 hour for all trips except the last one. This speed is max dist. Then we can use this speed to compute the total travel time. Right, total travel time. If it is larger than the target hour, that means we must travel faster than max dist. Since traveling faster than max dist does not change the time spent on all the other distance except from the last one, we can find the speed, the desired speed directly by we can find the desired speed directly by analyzing the requirement on the last trip. Otherwise, if max dist results in a time smaller than the target hour, then the desired speed must be between 0 and max dist. For that, we use binary search. Right, binary search. Two tricky parts. First, there is a need. Maybe we don't have to. We can just say, yeah, I just realized actual smaller than target. I can just say actual larger than target, right? If the actual is larger than target, then we return path plus 1. Otherwise, return part. So we have to. We don't need to consider. Ooh, that is not right. That is not right. Grr. If the actual is larger or equal to, if we say larger or equal to, I mean equal to is not available. We do this. Huh. How would this, are you saying actual is larger than target? I think actual is what? Actual is 0.01. Target is 0.009, right? Ah, actual is larger than. Oh, there's no avoiding it. We have to use, yeah, first, we must use, right, we must use math that is close to compare floating numbers, right? Second, actually, so I use math. Maybe the actual answer doesn't use math, the comparison. What's the second part? The second part is during binary search, right? During binary search, the computation of the total hours taken is different for the last distance compared to all the previous ones. Previous ones use math.ceiling, but the last one has to compute the actual, right? Compute the actual floating number. So this is O1 log n, right? Where n is the length of this. Well, actually, On max dist, right? O1 log n then. It's log n, and n is the n equals last max dist. It's running 2292 milliseconds. Surprisingly, we scored a 93. Okay. So take a look at this, take a look at this. Yeah, binary search, binary search, and binary search. I guess you can do binary search directly. Coco eating bananas. Is that the monkey? I think I've seen this before. Coco eating bananas. Oh, come on. Come on, browser. So slow. Coco eating bananas. Coco loves to eat bananas. Have I done this before? No, let's do Coco eating bananas tomorrow. N piles. No, I shouldn't read this. I should be saving for tomorrow. Who's Coco? Gotta be a monkey. Oh wow, it's spread all over the place. Alright, so apparently this binary search does not have to consider the special case. Oh, because you set a maximum. Now I see what you're doing. I see what you're doing. Ah. They say the maximum. Yeah, 10 to the 5th. I mean, you're basically guessing, right? The maximum. Well, we can guess. What will be the fastest? Oh, fastest. You never know. Fastest will be 10 to the 5th, right? Divided by 0.01. That is the fastest. So, actually, solution 2, I don't have to go through all the trouble, right? So, solution 2, binary search, but with a real high bound. Since dist I is smaller or equal to 10 to the 5th, right? That's smaller or equal to 10 to the 5th, and our only keeps 2 decimal points. Thus, the high bound for speed is 10 to the 5th divided by 0.01, which equals to 10 to the 7th, right? Thus, we can start from 10 to the 7th and not worry about the special case, right? Not worry about the special case that involves math.isClose. So in this case, we can simply just do this. No need to do this. And high is now going to be this. High is going to be 10 to the 7th. And then everything else will be the same. Let's see. Yep. Yep. It's probably will not be as fast because it doesn't have like the pre-processing stage. Yeah, it's not as fast. It's not as fast, right? It's not as fast. It's not as fast because we do not pre-process. We cannot pre-process the case when speed is larger than max dist, but the algo is simpler. And we don't have to use stupid math.isClose. Yeah. I think this shall do. Yeah, it's low equals mid plus 1. Okay, this one runs in this 31 milliseconds or a 84. All right, I don't think it's worth it posting anything. Everybody is doing binary search, so that shall be it. That's the cheat sheet on when to +1 and when to -1, right? Yeah, I think I'm leaning towards this. This is gonna be small, and we are always low, mid +1 because we are trying to unbias this part. Anyway, that will be it for today. We did well. We did 2 questions. I'll see you guys tomorrow. Adios.